Today's lesson is on the intermediate value theorem and end behavior. The intermediate value theorem describes a key property of a continuous function. So basically what the intermediate value theorem is saying, it's saying that if you have point A right here, and you have point B right here, then there has to be at least one point in between them. In this example, I labeled it point C. So it is a pretty basic theorem. When you read the math definition right here, it's going to sound a little crazy, but it's telling you that if you have point A and you have point B, you have a point in between them. So if we have 2 points connected by a continuous curve, like this line here, our 2 points are A and B. Let's just mark the x-axis as a line just for reference. So if we have 1 point below the line, that would be point A, and another point above the line, that would be point B. There will be at least one place where the graph crosses the line. That's this point right here. Let's label that point C. Point C is where this curve crosses the line I just labeled in green. In the first example set, we're going to use the intermediate value theorem to approximate zeros. The directions tell us to determine between which consecutive integers the real zeros of each function are located. Quick reminder, when it's asking for consecutive integers, it's saying between which consecutive integers. It's asking you for x values. So our function is f of x is equal to x cubed minus 4x plus 2. And this is the interval that we're testing. So we want to know on that interval, so between those two values, where does the graph cross the x-axis, or where are the real zeros? Okay, so when I solve a problem using the intermediate value theorem, I like to make a table of values. I like to list all my x values. I'm actually going to make a horizontal table just for explaining purposes. And I'll list my output values, in other words, my y values. And then I'm going to test every integer on the interval of -4 to 4. That means I'm going to test in the function an x value of -4, an x value of -3, -2, -1, 0, 1, 2, 3, and 4. All right, when I test all of these, I'm testing them in the function. So I am taking -4. I am substituting -4 into this function, and I am solving for x. So for the first one, obviously -4, we would evaluate this function at f of -4. We would simplify it as -4 to the power of 3 minus 4 to the power of -4 plus 2. And we would simplify that. Our output would be -46. If we evaluated the function at -3, that means we're substituting -3 in for x, and our output here would be -13. -2, our output would be 2, -1, 5, 0, 2, 1, -1, 2, 2, 3, 17, and 4, 50. These are ordered pairs. So thinking about our ordered pair, This is our X column. This is our Y column. We need to think to ourselves, all right, where does the graph cross the X axis? And that would be when your Y values change from a negative to a positive. So wherever you see a change from negative to positive, like right here, that means the graph is going to cross the X axis. Let's just take a look at those 2 points on a graph really quick. So I'm going to look at these 2 points. If I was to graph a point at -3, -2, I would be right here. If I was to graph another point, -2, +2, I would be right here. If I was to connect those lines with a curve, it would connect like that. That means the point crosses the x-axis in between those 2 points. So anytime your graph changes from a negative to a positive, that means your graph is going to be crossing the x-axis, and that is going to be one of your answers. All right, looking at our chart of values, where else do we have a change from negative to positive or positive to negative? And I can tell we have one right here. That means we have an x-intercept between these 2 values. Oops. All right, and we also have a change in values between -1 and +2. That means we have another y-intercept between these values. So we have 3 changes. We have 3 changes from negative to positive or positive to negative. We would write our answer as a list, and we would say that real zeros occur between the points, and I'm using x points. So real zeros occur between the points -3 and -2. They occur between 0 and 1, and then again from 1 to 2. Okay, just a quick reminder, these are all of your x values, or they are consecutive integers. Okay, quick recap. When using the intermediate value theorem, you're going to be given an interval. The interval is listed somewhere next to the function, like this one. Test every integer value in that interval. That would be our x values. Substitute them into the function, solve for y. Wherever you have a change from negative to positive or positive to negative, that's indicating that there's a 0. And we prove that on our graph right here, where we graph 2 points, and we can see that there is a point that crosses the x-axis directly in the middle of them. Okay, please try the on your own by yourself. Answer is posted on my website. Okay, end behavior that approaches infinity from a graph. It's the first one we're going to look at. So you probably remember end behavior from Algebra 2. But end behavior is the degree, or found from, the degree and the leading coefficient of a polynomial. So these combine and they give you what we call end behavior. So end behavior of a function describes the trend of the graph if we look at the right end and to the left end. So you are literally looking at just the ends of the graph. You don't care what happens in the middle. And that's why in these 4 examples, you can see that I just gave you the ends. Whatever happens in the middle is fine. but we only care about those ends. All right, so the first example says that if x approaches positive infinity, the function approaches positive infinity. That means as you head towards positive infinity on the x-axis, the function is heading up towards positive infinity on the y-axis. If x heads towards negative infinity, the function still heads towards positive. If we head towards negative infinity on the x-axis, the function is still heading up towards positive infinity on the y-axis. That means anytime you look at a graph and you have two ends that face up, it corresponds with this end behavior. For the next one, if x approaches positive infinity, the function heads towards negative infinity. As we move this way on the x-axis, the function is heading down. And as x approaches negative infinity, the function approaches negative infinity. That means as we head towards negative infinity on the x-axis, on the y-axis, the function is heading down. As x approaches positive infinity, the function approaches positive infinity. And as x approaches negative infinity, the function approaches negative infinity. And the last case, there's only 4 cases. So the last case says that as x approaches positive, the function approaches negative infinity. And as x approaches negative infinity, the function approaches positive infinity. All right, here's our 4 cases from the graph. When doing end behavior, you're just matching. So take a look at the graphs I gave you in the example, figure out which one of these graphs it goes best with, and that's your end behavior. For this first one, number 1, looks like we have the graph heading up over here and heading down over here. That means as x approaches positive infinity, you always start with the x value. So as x heads towards positive, the function is heading upwards towards positive infinity on the y-axis. That tells us as x approaches positive, the function approaches positive infinity. And as x approaches negative infinity, the function is heading down, so it's getting lower on the y-axis towards negative infinity. As x approaches negative, the function is approaching negative. Number 2, both ends of our graph face up. As x heads towards positive infinity, the graph heads up. And as x heads towards negative infinity, the graph still heads up. So as x approaches positive, the function approaches positive infinity. And as x approaches negative, the function still goes towards positive. Both end behaviors head towards positive infinity. Okay, end behavior that approaches infinity from a function. So when you don't have a graph, you can tell this by the degree and the leading coefficient of a function. As a quick reminder, if we look at something basic, let's take a look at a basic function such as f of x is equal to 3x squared plus 6 in this function, this value of 3, that is called the leading coefficient. And I always abbreviate leading coefficient as LC, just to save me some time of writing. So leading coefficient is LC. This number right here is called the degree. And the degree is always the largest exponent. So knowing those two things, knowing what the leading coefficient and the degree is, will tell us what the end behavior is. First example, we care that we have a leading coefficient of 1 and a degree of 2. What we specifically care about is that the degree is an even number and that the leading coefficient is positive. So you have two choices. For degree, you have even or odd, and the leading coefficient, you have two choices, negative or positive. So if the degree is even, and if the leading coefficient is positive, that is all we need to know, then our end behavior tells us that both ends of the graph are going up. Both ends of the graph are heading towards positive infinity. Our next example, we have y is equal to negative x raised to the 4th power. This would technically be negative 1x raised to the 4th power. Our degree is a degree of 4, which is an even number. Oops. And our leading coefficient is negative 1, so it's a negative value. Whenever you have an even degree, negative leading coefficient, both ends of your graph are facing down or towards negative infinity. All right, this side of the graph that I just marked, or just drew a pink square around, these indicate that your function is an even function. Oops. So if the function is even, then both ends either face up or both ends face down. To repeat that, if you have an even function, even degree function, both ends face up or both ends face down. That leads us into odd degree functions. So odd degree functions would be when you have something like an exponent of 3. If you have an odd function and a positive leading coefficient, then as you head towards positive infinity, the graph heads up towards positive infinity, and as you head towards negative infinity, the graph heads down towards negative infinity. If you have an odd degree, a negative leading coefficient, then as your graph heads towards positive infinity, the graph is going to head down towards negative, and as your graph heads towards positive, your graph will head up towards positive. Okay, so for an odd degree functions, the ends face opposite directions. So one will head towards positive, one will head towards negative infinity, but always opposite directions. All right, unfortunately, actually, fortunately for you guys, you don't have to memorize this table because this year's open notes, but in the past you would just have to memorize these. I do think it's still a good idea to memorize them so you can do it a little bit faster, but it will be open notes. If we take a look at our two examples, remember all we care about out of the whole function, all we care about is the degree and the leading coefficient. So for number 1, we have y is equal to negative 3 times x to the third plus 4x minus 6. In this example, the degree is a value of 3. That tells us that the degree is odd. Our leading coefficient is negative 3. Negative 3 tells us that our leading coefficient is negative. I'm going to take a look at my chart that we just filled in above. Whenever the degree is odd and the leading coefficient is negative, you would be in this category here. And that tells us that as x approaches positive infinity, the function approaches negative, and as x approaches negative, the function approaches positive. That's our end behavior. That's our answer. It's kind of like a matching thing. So do you understand what end behavior is, and do you understand how you find it or how you identify the degree and the leading coefficient? Number 2, we have a degree of 2, a leading coefficient of 8. A degree of 2 would be an even number, and the leading coefficient of 8 is a positive number. We look at our table above. Where is the degree even and the leading coefficient is positive? That would be this category I just highlighted. And in this category, as x approaches positive, the function approaches positive infinity. And as x approaches negative, the function approaches positive infinity. We'll fill our answer in with both ends heading towards positive infinity. And that's it. All right, the last section, end behavior that approaches a specific value from a graph. So when it doesn't head towards positive or negative infinity. Recall that some graphs, specifically rational functions, could have a horizontal asymptote. And a horizontal asymptote is a horizontal line that the graph approaches, but it never touches or crosses. And you can see that in this function here. This function is coming up to that red dashed line, but it is never touching it or crossing it. If a graph has a horizontal asymptote, then the end behavior approaches that line, meaning the line of the horizontal asymptote, and not infinity. Okay, we do have to quickly go over horizontal asymptotes for this to be effective. Horizontal asymptotes are very simple. You just need to understand what we're looking at. It is a topic from Algebra 2. You might remember it. But a horizontal asymptote is found when you compare the degree of the numerator with the degree of the denominator. There's 3 choices, or I should say 3 cases. And for all 3 cases, you're looking at the degree of the numerator and the degree of the denominator. I labeled the degree of the numerator in this notation as n and the denominator exponent as m. But if I give you an actual example, let's use an example of f of x is equal to 5x squared over x cubed. All right, so number one, or the first potential case, if n is less than m, so if the numerator exponent is less than the denominator exponent, then the horizontal asymptote is automatically at the line y equals 0. For the second example, if n, or the numerator of the exponent of the numerator, is equal to the exponent of the denominator, then the horizontal asymptote is at the line y equals a over b, or the leading coefficient of the numerator divided by the leading coefficient of the denominator. And the third potential case would be if the numerator degree is larger than the denominator degree, then there is no horizontal asymptote. In that case, there would be an oblique asymptote, but we're not going to look at those quite yet. We look at those a little later in the year. So in the example that I wrote off to the side, we have an exponent in the numerator of 2 and an exponent in the denominator of 3. That would fall under this first category where the numerator degree is less than the denominator degree. That tells us automatically that our horizontal asymptote is at y equals 0. Now, when you're looking at these, you can kind of tell where the asymptote's going to be because you obviously have the graph in front of you. But I also made sure I always gave you the function so you can confirm where that asymptote is going to be. In the first graph, we have f of x is equal to x over x squared minus 2x plus 8. The degree of the numerator is 1, and the degree of the denominator is 2. 1 is less than 2. That would also fall under this first category where the numerator degree is less than the denominator degree. So right away we know that this horizontal asymptote is at the line y equals 0. Based on what we read above in this box here, if there is a horizontal asymptote, then the graph approaches that line and not infinity. So here we would say as x heads towards positive infinity, the function is heading towards 0. It's heading towards that asymptote. And as x approaches negative infinity, the graph is heading towards 0 again. Both ends of this graph are heading towards that pink line I drew. And number 2. We have the function f of x is equal to 3x minus 2 divided by x minus 1. Well, the largest degree of the variable in the numerator is 1, and the largest degree of the variable in the denominator is also 1. That means we have 2 degrees that are equal. So a degree in the numerator and a degree in the denominator that are the same. That's the second case that I just highlighted. And it says to set up a fraction, this fraction, which is a over b, or the leading coefficient of the numerator divided by the leading coefficient of the denominator. The leading coefficient of the numerator is 3, and the leading coefficient of the denominator is just 1. 3 over 1 simplifies to 3. So our horizontal asymptote is at y equals 3. That means as x approaches positive infinity, the function is approaching 3. And as x approaches negative infinity, the function is approaching 3. We're only looking for the ends that head towards positive infinity on the x-axis and negative infinity on the x-axis. So we're looking for specifically the ends that head in those 2 directions. And both of these ends are approaching this line right here at x equals 3. They are never going to touch or cross that line. Okay, on your own answers are posted on my website. Just to give you a heads up, number 1 is going to approach a horizontal asymptote. So one of them does exist in number 1. And number 2, both ends of this graph head towards positive infinity. So number 2 is heading towards positive and negative infinity.